Yeah, I think that will be clear. So is that fine now?
Now it's fine.
All right.
Yeah.
So sorry, a bit late today. So we discussed yesterday that electromagnetic wave for a single frequency and certain direction of propagation, if it is like a traveling wave, it can be considered as it is normally designated as a monochromatic optical mode. So monochromatic optical mode, and that is the representation for a particular instant of time. And in fact, if you just plot that as a function of time instead of x for a particular position, then also you will see time dependent variation also sinusoidal. And at the same time, we introduced this particular equation. I will be coming to that particular point. That is called so-called one-dimensional Schrodinger wave equation for a quantum particle of mass m undergoing through a potential, so-called parabolic potential, defined by half m omega square x square. As a function of x, it is like a parabolic function. This is the potential energy, and this part is called kinetic energy. So total energy can be represented by 1D Schrodinger wave equations. So if you solve, I will just derive this equation also in course of time. Then you can find the solution for the energy of that quantum particle. Specifically, if it is in parabolic potential, and its motion can be represented by a motion of a harmonic oscillator, since it is quantum mechanics. So Schrodinger wave equation, it is used to solve. So the motion or this wave function, so called psi x, can be called as a state of the wave function of the particle, quantum particle, and the energy solutions will be in this form. So that is actually you have to keep in mind that this h bar, basically h bar is nothing but that is the reduced Planck constant, whatever earlier we have introduced, 6.626 into 10 to the power minus 34 joule second, and it is normalized by 2 pi for angular momentum here, omega. So that is basically omega equal to 2 pi nu. That means it is h nu. Basically, it is energy. And with that, you have a factor that is actually n plus half. So n is an integer. And what is this omega here? Omega is the characteristics frequency of the classical frequency, you can say, classical frequency of the harmonic oscillator. That's omega. And in this case, we define it as a square root of k by m, where k is called spring constant. So that spring constant, you can imagine that any mass m, if it is connected to a spring and with a rigid wall, and then if you apply a little force, then the force, you can say that it follows the Hooke's law, F equal to minus kx. And then if you try to see, if you are just giving a force, then it stores some potential energy, and that potential energy will be half kx square. So half kx square potential energy, and in terms of omega, if you replace that k value, then it will be coming as half m times omega square x square. So this omega is nothing but a characteristic frequency of the simple harmonic oscillations. So the oscillation frequency, I would say. If it is just sinusoidal oscillation, then that is omega. Okay. So in this case, you remember that we are not talking anything about time dependent part, but we are getting a solution, energy solutions. Why time dependent part is omitted here, we'll come to that point a little while later. So for the moment, you just concentrate that the solution of this energy solution of this equation, eigen solution I would say, is actually it's quantized. So n can be integer, it starts from 0, 1, 2, 3, 4 and so on, positive integer you can consider. So now here this energy actually it is shown here. This red color parabola, if you see, that is nothing but the potential as a function of x. X is the axis here. So as a function of x, because it is half m omega square x square, it goes like this. Okay, both negative, it is symmetric to the x-axis. And the energy, if you get a solution of the energy of this kind, that energy solution will be like this. So when n equal to 0, then it is called E naught equal to half h cut omega, and n equal to 1, n equal to 1 means 1 plus half, so 3 over 2 h cut omega, 5 over 2 h cut omega, 7 cut 2. So with this is the solutions you will be getting. So you just note down that the energy is quantized. So that means the harmonic oscillator, if it accepts energy, it is again something not continuous, it is quantized. It can accept energy half h omega, and then next higher level energy is 3 by 2 h cut omega, 5 by 2 h cut omega. So it's kind of, it accepts energy in a quantized manner. And this separation between any two energy state, energy value, if you just see any two successive one, suppose E4 minus E3, you see that is h cut omega. Similarly, E5 minus E4 is equal to h cut omega. So it is something, h cut omega means h nu. So it is similar to what we observed for black body radiation, that energy is quantized in an electromagnetic wave like h nu or h cut omega. So here also it is quantized like this. Okay, and for each energy eigenvalue, you will get a solution for psi, a space-dependent solution. And for example, when n equal to 0, the solutions will be almost like it's like a Gaussian, right? And then normally all other solutions, if you can find, they will be actually Hermite Gaussian. So it will be just one maxima there, you will be getting 2 maxima, 3 maxima, and so on. It's kind of be distributed. So one thing you should keep in mind that any harmonic oscillator, the solution of this so-called wave function psi in one dimension, that actually spreads as its energy increases, energy value increases. So that distribution will be different for different energy state solutions. So that is actually well known in quantum mechanics, a basic quantum mechanics book. If you see that this is the solution will be coming. So one important part is that when n equal to 0, that value half h cut omega, you can't get lower than that energy is there. Lower energy can be 0 when it is not in motion. Once it is in motion, then energy will be, next level energy will be half h cut omega and so on. So this particular value is called 0 point energy, and this distribution will be calling as a ground state. Okay. Now, I said that here any harmonic oscillator, if you just try to recollect your school level knowledge, any harmonic oscillator, you have, for example, a simple example is a pendulum, and in the pendulum solution, you have observed there that the kinetic energy and potential energy, total energy, that means kinetic energy plus potential energy is conserved. So when potential energy is maximum, that means your kinetic energy is 0. And when kinetic energy is maximum, then potential energy is 0. So total energy is conserved. So basically in entire motion, when it is in motion, that means it is in kinetic energy will be there depending on its velocity. So energy of the system, total energy of the system, basically shuttle back and forth between potential energy and kinetic energy. Okay, that is the take-home message for the moment here. any harmonic oscillator, the energy, total energy of the system, suppose it is oscillating at this point, with this total energy 3½ h card omega. That means this is the maximum energy. This maximum energy will be flying back and forth between potential energy and kinetic energy, and it can be shown, will be showing in course of time, that any monochromatic optical mode is basically can be represented similar to like this quantum harmonic oscillator. But here, in a pendulum example, or spring oscillating, a mass oscillating with a spring, the potential energy and kinetic energy goes back and forth. So similarly, here also we can show that the energy of electromagnetic wave, when it propagates, so that energy actually shuttle back and forth between electric field and magnetic field. That is what we have learned earlier also, that you can consider this electrical energy actually stored in a medium. Can be free space also, but that medium, as if you can consider that medium is a comprised of capacitor and inductor. So if it is lossless, sigma equal to 0. So in that case, electrical energy stored in the capacitor, it is like half epsilon E square, and magnetic energy is stored in like an inductor, so half mu H square. So that means when it propagates, it behaves as if that energy is shuttling back and forth between capacitor and inductor. In other words, energy is being shuttling back and forth between electric field and magnetic field. So if you can try to show that this is also similar type of things, so one type of energy moving to another type of energy, electrical energy moving to magnetic energy, and magnetic energy again moving back to electrical energy. So in this way, actually energy propagates. So it is, if you just compare with harmonic oscillator, there are also potential energy and kinetic energy, you say. So if you solve this equation quantum mechanically, as you have done for your simple harmonic oscillator, so-called quantum harmonic oscillator, there also you will find in a particular mode energy. This is not electric field. This energy now I am calling as a energy of this mode, total energy of this mode. That can be represented also in a similar way. Here En equal to h card omega n plus half. Here also we represented the energy of the mode is equal to n plus half h card omega. Clear? So that is just qualitatively, you just accept it for the moment. Okay, because this will help you to understand some mathematical formulations will be coming in next stage. So now you just try to little bit visualize qualitatively that here energy is this one, and when n runs from 0 to 1, 2, 3, 4, then it goes to higher state energy. But here energy also represented by this one. Here also you have one integer value. So what is this integer value? If you just increase the n, that means you have n number of h card omega. But you know that when n you are increasing, your frequency is not increasing. It's the same monochromatic mode, same frequency. So what is this n then? Suppose you are considering electromagnetic wave propagating here, monochromatic optical mode, and then its energy quantum mechanically, if you solve it, it is represented by this one. And you know h card omega or h nu is the photon energy. Now what is this n should be? Anyone can answer?
Photon number.
It is a photon number basically, because you can think of that if E field magnitude is increased, then energy increases. And when energy increases, then you can imagine that basically energy always, we have learned that energy is concentrated in a fundamental unit like a photon. So this n here actually represented the number of photons in that mode. Clear? So you can see that any mode, monochromatic optical mode, when electric field strength or magnetic field strength is increasing, that means you can imagine that number of photons are increasing in that particular mode. Okay, now I suggest you to just think about just a Gedanken experiment or thought experiment. Suppose you have a mode like this. So you can imagine this mode can be a cavity mode. That is also true. When this field is extended from -infinity to +infinity, that is called a mode also. Or you can actually fold this traveling wave into a cavity resonator. That means you have a reflector in both sides, and then it is can go back and forth, and round trip, if it is a phase change of 2 pi, then that can be also sustained. So as if it is traveling infinitely, you have some kind of boundary, fixed boundary is there. Within that boundary, it reflects back and again reflects back and go back and forth, and you get a cavity type things. So you get a traveling wave can be represented as if like a standing wave in a resonator. So that is just, you are thinking like that. That is possible. That entire wave you can just hold within a cavity. It's a traveling wave when you hold within a cavity and maintain the condition that round trip is 2 pi phase, then energy can be stored, and that energy strength depends on actually how many number of photons are there in that cavity. Right? Now you think that, okay, you have a cavity, and suppose that inside the cavity there is electromagnetic energy. Resonator is there, and n number of photons are there, right? And you know these photons from the knowledge of our photoelectric effect or so-called spontaneous stimulated absorption, spontaneous absorption, etc. When this electromagnetic wave give up some energy to some material, so it gives in a discrete manner, photon by photon counting. So suppose you have some kind of tool to actually take out the photons one after another. Suppose n is, for example, it is 1000 photons were there. Okay, all are same frequency in the cavity, 1000 photons were there. Now we have some kind of tool that you can pick one after another photons. So you are picking all the photons out of the cavity. 1000 photons you have taken out. Then what is there? There will be 0 photons. But what is the energy there? That will be half h cut omega. Even though you drain all the photons from the mode, so-called monochromatic optical mode, you end up with a energy of half h cut omega, that is equivalent to 0 point energy of the quantum harmonic oscillator. Okay. Now if you see that half h cut omega belongs to this mode, but this mode, what is the frequency? Omega. So omega frequency, but you have some energy called h cut omega by half, 2. So that is not a single photon, that is a half of the photon in principle, mathematically if you see. But half of that photon cannot exist in that mode, right? So what is that? So this is some energy. It is not really accessible to you. But quantum mechanical solution gives you that energy, that solution that exists. And in fact, experimentally, it is also found that this energy existence is there. And because of that, you see a lot of phenomena that is experimentally observed. Now, since this photon is not, this is not a photon at all, but this is energy, I would say, 0 point energy. So what we could do that, what is the corresponding electric field and magnetic field for that energy? You know, classically, if you have energy, you know that energy flow E cross H, pointing vector, everything. So if energy is known, then you can find out at least the strength of electric field and magnetic field. Now you convert back this energy into electric field. and we call that electric field as a E vacuum. That is a field now, this italics, E, vacuum field. You can express that is actually h cut omega by 2 epsilon 0 V. V is called the volume of the resonator. We'll come to this point how it is coming, but for the moment you can say that resonator volume is V, and this energy, half h cut omega energy, is distributed everywhere. And then you can imagine that in the resonator there are two orthogonal polarization is there. One is TE polarization, another is TM polarization. And we can say that this energy distributed into both the polarization classically, then corresponding electric field in the vacuum can be represented by this one. If you look into this equation, this is not a photon. Though h cut omega is there, but h cut omega by 2 is there, so it is not a photon basically. So it is some energy, and that corresponding field strength is there, this one, and you can also estimate what is the magnetic field strength from the Maxwell's equation, corresponding. But if you see that B is the volume, suppose this volume of the resonator is very large, B is very large, so this vacuum field strength is very small. When B tends to very small volume, say nanoscale, nowadays nanotechnology, you can go down to nanometer scale. So in that case, this vacuum strength will be very high, electric field vacuum strength. Okay, so you have this vacuum field or vacuum energy is there, but as I said that this is something not accessible, but this is there. But in terms of photonic point of view, what this field, where from this field coming, where from this energy is coming. So it was speculated that, as I said, that even no photons are there, that is spontaneously in the cavity, there will be random photon generation and destruction of these photons. As a whole, if you take average, you will get that average, this amount of energy is there. So energy is half h cut omega, so you cannot access that energy, but it's a constant generation of photons and their destructions is happening, and on an average you get this type of energy. So that is happening spontaneously, and that is so-called what Einstein explained is fluctuation, photon fluctuations, quantum mechanical fluctuations, first term and then continuous second term was there. So this is actually called vacuum field fluctuation, vacuum field, and that will fluctuate. It is an average value and it will fluctuate, and this fluctuation also you can actually say that it's some kind of you cannot quantify. This fluctuation is due to the energy is not finite with the electric field as well as magnetic field. So some kind of you can apply some kind of uncertainty principle, and because of that uncertainty principle, this type of fluctuations will be there. Uncertainty principle, for the quantum particle, that momentum and position you cannot simultaneously measure accurately. So here also you can think of that certain kind of uncertainty rule you can apply, that you cannot measure accurately, but those are there, that existence is there, and that fluctuation, that uncertainty fluctuations actually responsible for all sorts of spontaneous emission in the, whenever there is a matter is there and any excited state is there, then you always see that even though that is a stable energy state, but if it is higher state and lower state is empty, that will come down. That will come down because of this fluctuation, this vacuum fluctuation. So all sorts of spontaneous emission or natural decay, if you see any system, any energy is decaying from a higher state to lower state, that is because of this vacuum fluctuations, which could be explained through quantum mechanical treatment. Okay, so now this is very important, and this is going to be a very important parameter for quantum photonics device analysis, as well as this one also. Whenever you are talking about single photon, two photon, all those type of things for different type of application, this thing will be there. So we'll be now trying to reach out to this stage, whatever qualitatively we discussed here, from a little bit of basic understanding, and then we go forward for technology, device working principle, and how to deal with them, how to deal with a single photon and how to manipulate them. That will be our next phase. All right, now you should keep in mind that we have to understand how this is coming, origin for this, and maybe a little bit of this quantum mechanics, because it is originated from the Schrodinger wave equation. I'll just quickly go through the Schrodinger wave equation, even though some of you may have learned in your school and also earlier courses, but I think quickly you should go through, and if you can't understand also, you can consult with a textbook. You don't need a very rigorous thing. It would be a very simple, straightforward understanding here. Okay. Now, so wave function psi. There you have. I have introduced actually psi, right, in Schrodinger wave equation. So this psi is something you are actually using that to actually represent a quantum state of a quantum particle. Okay, so basically the physical state of a particle is determined by this value psi. Here this psi is represented as a position vector and time dependent part. So whenever any quantum particle is there, in a quantum system you are treating, so you don't need to bother about anything else if you understand how to represent that quantum particle in terms of this psi expression. Knowledge of psi if you have, then you can actually use Schrodinger wave equation for its entire dynamics. Okay, so I write that the wave function psi RT is governed by Schrodinger wave equation. So we will be trying to this whenever this psi was introduced by Schrodinger himself, and he could actually derive the equation, but he could not interpret properly the psi. What is actually the psi? It is a function, but what is psi and what it actually gives physically could not be explained. And many people actually questioned about that, but he said that okay, whatever it is not explained, that is fine, but my equation is giving all the correct results. So later on it was actually interpreted, particularly there was several conferences happened among quantum mechanics stalwarts led by Niels Bohr in Copenhagen. From the Copenhagen interpretation, that interpretation came out basically actually led by Niels Bohr, but all other quantum physicists also participated, like Heisenberg and Niels Bohr, Heisenberg and Dirac and many other people. Okay, so from that interpretation, okay, whenever it is quantum particle, we always say that is a size is point like size, but in fact it has certain kind of point like means you cannot really determine its position at any instant of time at any particular coordinate or something like that. So instead we define a parameter called probability, that finding the particle in a certain point, it's not very much certain, rather we just define with a probability function. So we say that the probability of finding the particle in a differential volume.
Sorry, sir. CSD 400.
I'm in a class. So the probability of finding the particle in differential volume dV is given by this is so-called P RT and multiplied by differential volume dV. So that means we can call this PRT as a probability density. Probability density, you multiply by volume dV, then you get probability of finding the particle, quantum particle in that volume dV. And this PRT is defined by psi RT mod square. Basically, why this is mod square? Because you see, whenever you will be going through the Schrodinger wave equation, you will find that the psi RT is not a real function. The necessary condition is for psi is that it should be complex. So this complex function, there is no physical reality. But if you take complex conjugate and multiply, then whatever you get, that is actually called the probability of finding that particle at that particular position. And that is probability density. And multiplied by dV, you get the... Of course, if you just integrate this probability density over entire volume, then probability of finding should be 1. If you integrate minus infinity to plus infinity entire space, then this should be 1. So psi can be actually normalized to that, so that psi function, whatever psi function you introduce, that should be normalized such that it should be minus infinity to plus infinity. If you integrate, it should be 1. So basically, since the quantum particle, we don't have proper knowledge how it behaves, right? We express with a function, but that function, with that function, we impose a lot of condition while solving, so that we can actually get our practical results out of the quantum system. So that is one of the interpretation comes out that this probability with psi, that probability density represented by this equation 22. Now, according to Schrodinger, the equation of motion of the quantum particle, actually the equation of motion of that quantum particle, while deriving, it took the knowledge of classical idea. You know Hamiltonian, I said yesterday. The Hamiltonian, we define as a Hamiltonian here. Hamiltonian is nothing but total energy, kinetic energy as well as potential energy, total energy. And since psi RT is it's a physical state of the quantum particle, instead of direct Hamiltonian, we call that Hamiltonian operator. It is a function. So if you operate on Hamiltonian operator, you apply to this wave function, then you get this function. This is another operator and returns with the same function. That is called I h bar del del t. So that was the Schrodinger wave equation. Okay, so Schrodinger actually brought down this equation. He took the knowledge of classical physics, all those type of things, but writing down this equation, while explanation, etc., if you sought for, he was actually completely blind. He could not explain where from this is actually coming from this to this. Later on, from the various aspects of various solutions, assumption you consider, and then we prove that, yeah, this is correct. So here you see that psi is our position dependent and time dependent. That's the physical state of a quantum particle. And we have a Hamiltonian operator. You operate and you get IH del del t, also same thing. This is actually Schrodinger wave equation. Fine. What is Hamiltonian? That is actually, in terms of operator, we write T, that means kinetic energy operator, and the potential energy operator. Okay, and this energy operators can be defined in terms of position operator. I think the energy operators, we see the energy position operator and momentum operator. Position operator you can write, because you see this psi is R and T, so you can actually define R operator, position operator. That means operator means if you operate on that psi, then you get actual position, so-called position, if anything at all is there. So that is basically, we write our position operator is nothing but it's a position coordinate. And the Cartesian coordinate system we can represent like this: ax, ay, az are unit vectors. And momentum operator, if you see, this is minus IH nebula. It's a vector, and this nebula in Cartesian coordinate system, we know that that is defined by this one. So other operating coordinate system also we can express, if necessary will come, but most of the time will be we are okay with this type of operator in Cartesian coordinate. Particularly whenever you are solving for atomic structure, etc., normally it is good to represent this nebula operator in a spherical coordinate system, r theta phi. I think in classical physics you know that how this operator, this del function is given. Fine. So now we come to some kind of how to get a solution, how to deal with this Schrodinger wave equation. First assumption, I think that is not a bad assumption. Potential energy in most of the cases you consider is time invariant. That means time independent, I would say. So potential energy only space dependent. So as a function of time, potential energy distribution is fixed. It's not varying as a function of time. But there are examples also the potential energy can be time dependent. So that will be coming later. For the moment, you can consider that potential energy is just space dependent. Okay. Then Hamiltonian operator can be expressed as, so you see first one is the kinetic energy. P is the momentum. So momentum square divided by 2m, half mv square. So that comes your kinetic energy, and then plus potential energy. So if you just write down as an operator form, so you just write a hat sign here. That will be equal to, again, P, you know, P we have defined in the previous momentum operator. P is minus IH del. So P square operator, that means minus IH del dot del. That means it will be minus h car square del square. So that is del square, h car square 2m del square, and VR as it is. So Hamiltonian operator in turn you can express like this. Del, again you know, del square means del 2 del x2, del 2 del y2, so scalarities. Okay, and this is the operator. Of course, it's a position dependent, and VR can be now, if it is Cartesian coordinate system, this R can be also written as Vxyz. Fine. So now from equation 23, we have Schrodinger wave equation for the particle of mass n. What is that? Equation 23, original Schrodinger wave equation. That is the 23 equation. So I am just inserting Hamiltonian operator, whatever I have derived there, I want to insert here. Okay. So after inserting this Hamiltonian operator in that equation 23, I get this equation. Left hand side and right hand side. Okay. So now thing is that we have to find out. We need to solve this equation. Ultimately, we need to know what is the nature of psi. So you just keep in mind that psi is a function of RT, and you can get a solution of this equation. This is second order differential equation, and partial derivative is there with respect to time. Okay, but this function psi RT actually heavily dependent on how is the nature of potential energy, VR. Okay, so suppose that is known to you, VR is known to you, potential energy is known to you. And then you try to find out what is the value of psi. And this type of equation, I think we have gone through many problems like this. You can actually solve by separation of variable. You can imagine this psi RT. Okay, psi RT is function of psi r multiplied by function of t, theta t. So if you just substitute here in equation 25 this psi value, then you get this equation where I have introduced a constant called E. Okay, at this point of time I am just putting E as a constant because this equal to this, that means each of them I can write equal to a constant E. So this one also equal to E, this one also equal to E, because they are equal. This part, left hand side, right hand side equal, and each side is equal to a particular constant I have introduced. Okay. So now from 26, okay, what we get? We get time independent Schrodinger equation. How we are getting? If you see left hand side, this one, there is no time. Psi r is there, Vr is there, del square psi r. So it is time independent part is there. And this side time dependent part. So if I write this one equal to E, then we call that is a time independent Schrodinger equation. And if you write this equal to this, that will be called as a time dependent Schrodinger equation. Clear? So we can get, by separation of variable, actually we get two differential solution equation. One is called time dependent and another is called time independent. So time independent equation I have written like this, 27. So psi r was 1 by psi r is there. So psi r I have taken this side. So this is a very nice differential equation which is only space dependent, no time dependence is there. And time dependent part you are writing this one, right? So equation 27 and 28, they are actually most important part. Sometimes we use that if time dependent function is well defined, well known, then we can actually find what is the space dependent function psi r by solving 27. And again, when we know that this is already well defined, psi r is well defined, and we can try to find out time dependent variations of the wave function, this one. So if you just compare this 27 and 28, I think this should not be partial anymore. D dt it should be, okay, because it is only time dependent function is there. So if you try to see 28 solution, you try to find out, it is relatively easier. This is a first order differential equation, only complex values there, minus I h cut, right? Okay, so if you solve that, that will be coming like theta t exponential E I t by h cut. What is E? So far we have not defined what is E. It is a constant. We consider so far it as a constant. Now if you see, this is actually e to the power minus I e times t by h cut. H cut is something related to Planck's things. And E, if you write down E equal to h cut omega, then what happens? This is e to the power minus I omega t. If you just think E equal to h cut omega, then this will be e to the power minus I omega t. What is that? In our classical electromagnetic wave, the traveling wave, when we define, the expression is e to the power, we wrote there j omega t minus kx or k dot r. So time dependent variation of the traveling wave is e to the power minus j omega t. So this E, if it is considered that the energy, if you consider this is the energy of this quantum particle, in fact, if you see, this is the kinetic energy part and this is the potential energy part and this is the total energy part. That way you can define. So E can be considered as a energy of the quantum particle. Okay, and it is actually sinusoidal, it is varying. From this equation you get directly. So any quantum system, if its energy is known, okay, then time dependent variation is known to you for sure. That's a straightforward. This time dependent part like this. So by chance you have some value known also VR, then you can solve also 27. Then you know entire solution for this psi will be like this. The psi r, whatever you are getting solution from 27 multiplied by psi theta t. So that will be the solution of the wave function. So any quantum particle, if you know what is the potential distribution, then you can actually solve psi, nature of psi. But nevertheless, this energy, it is considered as a constant, but that constant value, that means even though it is h cut omega, you are considering that omega you have to find out. That energy you have to find out, you have to solve that. So if you can solve simultaneously this equation 27 equation as a so-called eigen equation. So if you find a solution for one psi and corresponding E, that will be actually eigen function, and this is the eigenvalue solution. E will be eigenvalue. Corresponding to that psi, it will be 1E solution. If you have another psi, another E solutions will be there. So same quantum particle can give you multiple psi solutions and multiple energy solutions also. It's a differential equation, you know, differential equation when you solve, you can find multiple solutions. Okay, so now we come back to our in the first slide, whatever we have discussed, that one-dimensional Schrodinger wave equation we have used as a quantum harmonic oscillator. So this equation del square, if you are considering that your quantum particle is restricted for motion only in the x direction. So that means this del square, del 2, del y2, del 2, del z2, they will be 0. So only x dependence is there. So this equation 27 can be written as like this. Okay, so h cut square by 2m d2 psi x dx2 vx psi x e psi x. So E is the energy, and that Vx, whatever we consider it's a potential energy. If it is a simple harmonic oscillator or spring, the quantum particle is attached to a certain point with a spring constant like things, then you can find out that potential energy is half omega square x square. Then you can solve this thing to get whatever we have discussed here. This equation, whatever I have written here, that is actually shown there in one-dimensional case. So now we are done with the Schrodinger wave equation, and we have reached up to this point for 1D. 1D, actually all the practical system is normally three-dimensional, but it is easier to visualize by considering one-dimensional. Then you can actually consider what is happening in the three-dimensional case. Okay, so with this, I just maybe close today. I think a lot of things are there. If you have not gone through the quantum mechanics, you just this slides, this video record I will be again uploading, so you can go through that and maybe consult with some kind of basic books and try to visualize this thing. So only problem will be there that what is this psi, why we are considering psi, RT, all these things, because quantum mechanically it behaves completely differently, and it has not been actually developed in a day by Schrodinger. It was a long stories there. You can start from your Bohr's theory of atoms, molecular theory, and then de Broglie's hypothesis and some experimental observation, and then one day Debye asked Schrodinger, he was doing some other type of research. He was saying, what nonsense you are doing, this is a very interesting thing, why don't you try to solve this quantum nature of a quantum particle. So particle, when it is a microscopic size, then he came out with this equation, and it was now celebrated. Okay, all right, with this I just stop today. Thank you.